learned how to write a representation of SUSY algebra of n equal to 1 SUSY on fields, and we constructed a chiral supermultiplet of 3 fields: a scalar field, a fermionic partner, and an auxiliary field. And we learned how to write their transformation properties and an antichiral supermultiplet. Complex scalar field, a fermion partner, we call it chi bar, and an auxiliary field, we call it F star. These are the smallest multiplets that you can construct of these fields. Today we'll construct another representation, and we give it a name, vector supermultiplet. And the component fields in this supermultiplet will be a gauge field, A mu, a superpartner, fermionic superpartner, a Majorana fermion lambda, and an auxiliary field, we'll call it D. So you can call it photon supermultiplet because it has a vector field A mu. So photon supermultiplet. A mu is real gauge field. That's what describes the photon. There's no charge. So the fermion that we have here will have no charge. So that's why it's a Majorana fermion. So lambda is a Majorana fermion. Means no charge. And D is a scalar field, again real scalar field because complex scalar fields can carry electric charge. So D will be a real scalar field. We could try and set up their transformation properties constructively there like we did it for the chiral multiplet. But that's a long exercise, we will not do that. We'll just give the result and motivate the result. And then later we'll learn techniques, more general techniques of how to write supersymmetric representation over fields through superfields, and there we'll do the complete exercise and show the supersymmetric transformation rules that we give here are exactly what should be for such fields. So what should be the transformation properties? Under supersymmetric transformation, this is a mass dimension 1 object. It should convert itself into mass dimension 3/2. So it means convert into a fermion. So lambda is that fermion. So that's what it is. This is a vector, and this is in a half zero representation, half representation. This combination would be in half representation of the Lorentz group. But this has to be real. This object is not real. So we make it real by adding So it contains both lambda and lambda bar, which means unlike chiral supermultiplets, which transformed only under one type of supersymmetry, either on Q or on bars, or anti-chiral was Q bars, this will transform under both Q and Q bar. So that's why they have. And this is real. So let me take adjoint of this object. What is adjoint of this object is lambda sigma mu epsilon bar. That's adjoint of this piece. Adjoint of this piece is lambda sigma mu bar epsilon. So something I have not done right. Lambda bar adjoint. Now we have done these exercises, we can take it across by replacing sigma mu by sigma bar. This is an identity, but it changes sign. This is one of the identities I think we gave as an exercise sometime. So this is now epsilon sigma mu lambda bar. That's exactly this. So that's why it's real. Then we must now prescribe transformation law for lambda. Well, let me put alpha on it, because lambda is made up of two components, alpha is 1 and alpha is 2. So again it should convert itself into dimension 2 object, mass dimension 2 object. So let's introduce D, a mass dimension 2 object, real scalar field. And then it could also convert into a derivative of A mu. So normalization half sigma mu nu alpha beta epsilon beta times derivative of A. But this is a gauge theory, so it better be a derivative of A, which is a gauge invariant derivative of A, because this has no charge. It doesn't transform under U1 transformations. So then we must prescribe the transformation property of D. Epsilon bar sigma mu bar d mu lambda plus epsilon sigma mu d mu lambda bar. Now this object, by the same kind of an argument, if you do it, you realize that this is pure imaginary. So put an I. Take the adjoint of this, do the same kind of an exercise here. There's a plus sign here, and that would essentially change the sign. So that makes the complete prescription of supersymmetric transformations of this multiplet. So let me list again what I said in words. Mass dimension of A mu is 1. Mass dimension of lambda is 3/2. Mass dimension of epsilon and epsilon bar is -1/2. So this is -1/2, 3/2, so that together this is +1, that's what it should be. Similarly here. Now this is 3/2, this is -1/2. What should be the mass dimension of D? So like we said earlier, any object of mass dimension greater than 3/2 cannot be a physical field, cannot have a dynamical degrees of freedom, cannot have an equation motion with second order time derivatives. So this is an auxiliary field. That's a name we have given, auxiliary word we have used, that not dynamical or not physical. Now, we could, in order to make sure that this is, where is the eraser? Okay, it's here. We realized we have prescribed these laws, but these laws must satisfy supersymmetry algebra, which means they must satisfy if I take a variation with respect to supersymmetric parameter 1 and with 2 and take a commutator on these fields acting on any one of them, say on lambda or on D, that should give me minus 2I epsilon one sigma nu epsilon 2 bar minus epsilon 2 sigma nu epsilon 1 bar d mu derivative on lambda or D. So one can check and see if that's so, and it indeed is so. And we have fixed these various coefficients precisely that this property is true. Now it should not be, it should be true not only on lambda and D, but it should also be true on A. So if you do this calculation on A using these laws, what you get is minus 2I epsilon 1 sigma nu epsilon 2 bar epsilon 2 sigma nu epsilon 1 bar times d nu of A mu minus d mu of A nu. It is F nu mu, right? That's what F is. Maybe I should have written down here what F is. Now you notice that this is not exactly the form that we want. But let me do a little bit of break this into two parts. That part is fine, that's what it should be. There's an extra piece here. And rewrite that as these are constants, so I take the derivative out. And this object is just nu or contracted. This is just a scalar function. So this is d mu of a scalar function. So the algebra on A mu with the description that we have given here does close, but up to this point. So we'll write it in words. Algebra on A mu closes, but up to a gauge transformation. A gauge transformation on AX, that A mu I could write it as like, call this whole thing xi. So what you have noticed is that this representation does satisfy supersymmetry algebra, but supersymmetry algebra closes up to gauge transformation. But that's also an invariance of the theory. It will close. Yes, because F nu is gauge invariant. Okay. So that's one thing to notice. The another thing is to notice is, let's count degrees of freedom in this multiplet. Off shell. Off shell means we count degrees of freedom of the auxiliary fields also. We are not using their their constraint equations to eliminate them out. We are not using equations of motion of A and lambda. When we use equations of motion of A and lambda and D would be a constraint equation, then that will be on shell counting. That will count real physical degrees of freedom of the multiplet. Now we have 4 degrees of freedom in A mu and 1 in D, bosonic degrees, that is 4, 5 bosonic, 5 real bosonic, and lambda is made up of 2 complex objects, is 4 real fermionic. So there is a mismatch. Both these facts, this one and this one, that there is not matching of Bose Fermi degrees of freedom, is a reflection of the fact that the supermultiplet that we have written here is not a complete off-shell supermultiplet. There are in fact, one could introduce some more auxiliary fields in it to make it complete off-shell. And when that is done, then the degrees of freedom between bosonic and fermionic will be equal, and so also this property will not be there. The algebra will close without the gauge transformations. So this reflects a fact. This is not a complete off-shell supermultiplet. Complete means there are other auxiliary fields which we have not considered here. Why auxiliary only is because the following. Now let me count on-shell degrees of freedom. On-shell degrees of freedom means D is not a dynamical field, so we don't count them, only A, mu and lambda. And what are the on-shell degrees of freedom of a vector field? Satisfies Maxwell's equations. And on-shell degrees of freedom are only 2 in A mu. So 2 bosonic, 2 polarizations. And what are the on-shell degrees of freedom of a Majorana fermion? Instead of 4 here, the corresponding Dirac equation will reduce them to 2 real. So, which means the physical spectrum or physical degrees of freedom in the supermultiplet do have Bose-Fermi equality. All right. So that tells us this is a supermultiplet on its own, on-shell supermultiplet, but the off-shell representation that we have given is not a complete representation.
I thought to make this supersymmetry algebra close, you will do a gauge fixing. You will go to a particular choice of gauge so that mu also satisfies the supersymmetry. So if you do gauge fixing, then
we'll get to this issue, and I think he has put his finger exactly where what the origin of this problem is. The origin of problem is that all those extra auxiliary fields that we have not put in here are a gauge choice of the U1 gauge of this theory, and in that choice all those fields have been put in equal to 0. And that's why the algebra closes only up to gauge transformations on this reduced supermultiplet. We'll see it in detail when we do the superfield things, because we'll list the whole list of complete list of off-shell representation. Okay. But keep this in mind. Now that was photon supermultiplet. Not no A mu, that redundant degrees of freedom in off-shell supermultiplet. In addition to D, there are other auxiliary fields. Any gauge theories. Okay. We'll get to this point again in more detail. We'll understand why it happens. Now we put a photon supermultiplet here. A non-abelian generalization for this is straightforward. So let's write down the non-abelian generalization. So what would non-abelian generalization mean? Non-abelian generalization means that I would have a gauge group G, and I would have an associated gauge field A mu. A is the internal space index in the adjoint representation. In adjoint representation of G. Adjoint is self-conjugate representation. So, real representation in some sense. So, for example, SU2 there will be 3 of them, for SU3 there will be 8 of them, and then we need their fermionic superpartners. Fermionic superpartners would also come in the same representation. So, spinners, Majorana spinners, in adjoint representation. Then we would have dA auxiliary fields again in adjoint representation. So that would be a supermultiplet. And what will be the transformation laws? Simple generalization of that. Put an index AA there, that's it. Just simply put an index AA on what you have here. Except now, this is instead of F, you will have the field strength of the non-abelian theory. G is the coupling constant of the theory. FABC is the structure constant of the algebra of the gauge group G. Generators of the gauge group G. Then now this ordinary derivative would have to be replaced by covariant derivative. So that left hand side and right hand side are a gauge transformation. This changes like the adjoint representation, this must also change the adjoint representation. That can change only if there is a covariant derivative. While covariant derivative on lambda A is the ordinary derivative lambda minus G A F A B C A mu B lambda C. I think there is a, in my conventions, minus sign here, yes. Plus epsilon sigma mu B mu lambda bar. So that's our non-abelian supermultiplet. Now mass dimensions again count as the same, A mu A lambda A dA are 1, 3 by 2 and 2. So D is an auxiliary field. dAs are auxiliary fields. I rubbed off that one, but look at the one abelian theory. Notice that the supersymmetry variation of D was a total derivative or total divergence, and supersymmetry variation of dA is a covariant derivative, total covariant divergence, because D can be taken out. So we said that was also the property of F's in the chiral multiplet. F's transformed as total derivative. Here D's transform as total derivatives. So dA transform into or transformed by a total covariant derivative. And if I did the same, study the closure of the algebra, I would find the same property as I found here in the U1 theory, which is that the algebra will close on lambda and D, but A mu, well, it will close on these objects, but up to a gauge transformation. So algebra will close, SUSY algebra closes, but only up to a field dependent gauge transformation. We did not derive these laws systematically, we only have prescribed them. But there is a very efficient technique of deriving them systematically. That technique is called superfield techniques. We'll now develop a discussion of superfields. This is a small generalization, a non-trivial generalization of something we do very casually in ordinary field theory. We take two scalar fields, phi 1 and phi 2. Real scalar fields. We write them collectively. It's a pair of fields by one symbol, and one symbol is by writing them as complex superfields. So two real fields as one symbol as a complex field. And in order to do that, we do it through introducing a basis to distinguish the two fields, which is called I. I is not a number, not an odd number, but square of I is a negative number, is -1. So we have introduced a new concept of I. We give it a name, pure imaginary number, with the property that its square is -1. It is not a number. Similarly, or even for two real numbers, A and B, which is pair, we introduce a symbol of a complex number. Complex number is not a number, but it's this combination we give a name complex number. Now in complex fields, what have we done? In these two fields have some, not only they are two real fields, but they have also some different properties. In complex field, the real field is a scalar and imaginary part is a pseudoscalar. So in this one symbol representation, what we have done is we have given a collective representation for two objects with different parity properties. Is that clear? This is a shorthand and very efficient. We are so used to it, we don't even think about it, what we have done. Now what we are going to do is that we have this collection of fields in a supermultiplet, let's say chiral supermultiplet, phi x, psi x and fx. Set of three fields. They have different spins. Spin 0, spin half, spin 0. They have different mass dimensions. So we'll try to find a method. Is there a collective symbol we can write for them? It's a generalization of what we have done for writing a field with scalar and a pseudoscalar with different properties, because parity properties are different. Here we have a set of fields, again with different properties. They are different in spin. More complicated structure than this. Is there a collective name or symbol we can give them? And that collective name, we will call it capital phi, is called superfield. Now in this case, it was only the parity properties were different. So you could introduce an I with defining that under parity conjugation I changes sign, and that would distinguish. Here I have to introduce a corresponding analogues of I. So analogues of I, which have to carry the information of that these objects are different spin, or these objects are different representation of the Lorentz group. So the corresponding analog of I that I will introduce must carry Lorentz transformation properties. So this is done through symbols. Give them a name, Grassmann. Numbers. They are not numbers like I was not a number, and we give a name with a complex number, pure imaginary number. That's the name given to this. Here again, they are not really ordinary numbers, but they have some properties, so we just give them a name, Grassmann number, and give them a symbol, theta and theta bar, theta alpha theta bar alpha dot. They have to transform under Lorentz transformations. So they will have spinorial indices. So alpha is 1 and 2, alpha dot is 1 dot and 2 dot. So they carry Lorentz transformation properties. Not only that, they will also carry some mass dimensions because they are describing fields with different mass dimensions. So these transform under Lorentz transformation as half zero and 0 half representation respectively. And they have mass dimensions. So since they are half zero, zero representations, they are spin half objects. For spin half objects in field theory, we give an anti-commuting properties. So they will have to anti-commute. These anti-commute. That means anti-commutator of theta alpha and theta beta is 0, anti-commutator of theta bar alpha dot, theta bar beta dot is 0, anti-commutator of theta alpha, theta bar alpha dot is 0, and so on and so forth, whatever you can write. They have to have this property. Not only that, because they are spin half objects, these must anti-commute with any other fermionic object. And commute with any bosonic object. That is theta alpha psi beta. Let me take a fermion field. They must anti-commute. Similarly for theta bar with any psi or psi bar or chi bar, whatever you have fermions, they must anti-commute. But theta alpha with a bosonic field, they must commute. Let me write this part a little more detail, what we mean, so that we understand it here. What does this mean? This means theta 1, theta 2 is same as minus theta 2, theta 1. This also means that theta 1 times theta 1 is 0. So, or theta 2 is 0. And similarly, theta 1 bar dot times theta 1 bar dot, this is 1 dot, not I, 0. And theta bar 2 dot, theta bar 2 dot is 0. When that means is that each one of them, square of them is 0. But register that these new 4 thetas that we have introduced, they are not complex numbers. They are not ordinary numbers. They are some different kind of animals that we have introduced. We give them a name, Grassmann numbers, but they are defined by the properties that we have described. So the name that we give them name number in their name, put number should not confuse us. So after having introduced these thetas, now let me try to introduce object like superfields. What is a superfield? We can construct a superfield, and we give it a name, symbol here I have given it F, there I called it phi, here I will give it F, which is a function of x mu, 4 space-time coordinates, and is also a function of theta and theta bar. A function of theta and theta bar. I am using the word same function here. We understand what a function of real variables are, functions of complex variables are. But these are not functions of theta and theta bar the same way as we define functions of real variables and complex variables. Again, we use the word function in this context in defining an object f, which I will write down what it is, and use the word function for it. Or should I write it? Well, I have to read a longhand, so I need more space. So f of x, theta and theta bar something which is just an ordinary function, call it phi of x. Then something which depends on one theta. Phi of x is a bosonic field. It could be bosonic fermionic. In this choice that I have made, it's a bosonic field, and I have made a choice that it is Lorentz invariant. It is no alpha index. This object is Lorentz transforms under Lorentz transformation. So take a field, fermion field in half zero representation with one theta. This is a shorthand. See, we have used these kinds of notations, thought and that alpha up, psi 1 x. And I think I have normalized it by root 2 for some reason. So that is one theta piece. To this, if this is real, well, this is one, then I could also add a theta bar and call that chi bar x. That's also Lorentz invariant object. So I don't need these brackets now. Then I could add two thetas. I call it theta square. See, now I have used this theta square is shorthand for theta theta, which is theta alpha, theta alpha. Don't confuse as second component. In this notation, just to not write too many things, this is what it is, theta times theta, and that is theta alpha, theta alpha. Theta times theta, this kind of a notation is not 0 because this is theta 1 up, theta 1 is, that is theta 1, theta 2 in fact. And some object m of x, and simply theta bar square, and again theta bar square is shorthand for theta bar, which is theta bar alpha dot down, theta bar alpha dot up, the reverse of this convention. So 2 thetas. Then I could write another 2 theta piece, theta sigma mu theta bar times a mu of x. That's also a Lorentz invariant object I can construct with 2 thetas. I construct a Lorentz vector, contact with a Lorentz vector. Then 3 thetas, theta square theta bar lambda x bar, theta bar square theta zeta x. Zeta x is a fermionic object, this is a singlet, this is a singlet, plus 1/2 theta square theta bar square d of x. I think I have all the terms now. Okay. So what have I done? I have given a collective name f of x theta theta bar to this expression, which is made of phi x, theta times psi, theta bar times chi bar, theta theta times m, theta bar times n, theta sigma mu theta bar times a mu, 3 thetas, 4 thetas. I could write 5 thetas now, 6 thetas now, but I have not written them because 5 thetas will always contain a square of a particular theta component, and that by our definition is 0. Is that clear? You write the 5 thetas, one of the components at least will get squared up. So this is the only possible number of terms we can write here. And this is what we call function of x and theta theta bar. So this function of x and theta theta bar we call a superfield. So I have written a most general superfield that you can write in this theory. Now, if this was a scalar, this would be a fermion, a left-handed fermion. This would be a right-handed fermion. This would be a scalar. This would be a scalar. This would be a vector, which means spin 1 representation of the Lorentz group. This would be a right-handed fermion. This would be a left-handed fermion. This would be a scalar. I could make this starting one to be a fermion, then everything would change accordingly. I could make it a vector, then all these things will change. We'll get examples of those also while we're doing work. But this is the simplest one. And if I put mass dimension 1 on this, because it's a scalar field, so I take a physical scalar field. This is mass dimension 1. Mass dimension of theta is minus half. So this fermion is mass dimension 3/2. This is also mass dimension 3/2. Now what is the mass dimension of this object? Now what is the mass dimension of this object? A mu is 2, right? So this A mu cannot be a physical vector field, right? It's a vector field but not a physical vector field. And this lambda is 5/2. This zeta is also 5/2. And this object d is 3. So that's because I took this to be mass dimension 1. If I had taken it to be 0, then correspondingly there will be change. And if it was 0, then d would be mass dimension 2. And A would be mass dimension 1, right? So in that kind of a superfield, A could be given interpretation of a gauge field, dynamical gauge field, and D would be the auxiliary field, the kind of a thing that we wrote for the vector multiplet. Okay. Now is there anything else? Okay, now let me count degrees of freedom. How many independent fields are in this? Number of bosonic fields, number of real bosonic fields. Bosonic fields are phi x, mx, nx, a mu x, and dx. They are all complex. So 1, 2, 3, 4 complex fields, and a mu's are also 4. 4 is 8 complex fields. A mu is a complex field here in this way of writing. So that is total 16 real, because there are 8 complex fields here, 16 real. Fermionic fields. Fermionic fields, we have psi of x, chi bar of x, lambda bar of x, zeta of x, 1, 2, 3, 4. Each one of made of 2 complex numbers. So 8 complex numbers, that's 16 real fields. So this tells us that a superfield by construction has an equal number of bosonic and fermionic independent fields. It's by construction. That's a property of a superfield. Equal number of bosonic and fermionic degrees of freedom. Now, before I go ahead with more discussion about superfields, let me list some interesting properties of these various thetas, these Grassmann coordinates or Grassmann numbers that we have introduced. We'll also use the word, you see, these are space-time coordinates. We'll use the name for theta, theta bar as Grassmann coordinates. They are again not coordinates in the sense of that x measures lengths, breadth and height and time. Thetas don't measure any of these things, but we still use the word coordinate for them. Okay? So, Grassmann coordinates. And we will call, this is called ordinary space, this we will call superspace. The collection of x mu, theta and theta bar we will call superspace. So, now some interesting properties. These are very simple, but they are useful in doing calculations. Take theta alpha, theta beta, multiplied by theta beta, that is same as epsilon alpha beta theta theta. Remember what we meant by theta theta. Theta alpha up, theta alpha down, summed. This is very easy to check that so, because this is what we mean by this object, and this I can write as, this I can write as epsilon beta theta beta theta alpha, because epsilon, I can lower this through this epsilon, write it like this, and epsilon 1 2 is minus epsilon 2 1 is plus 1 in the way we have set up our conventions. So, now let me expand this. This is equal to 1 2 is plus 1. So, theta 2 theta 1 minus theta 1 theta 2. That is same as minus theta 1 and theta 2, minus twice, because they anticommute. You can raise and lower 1 and 2 by through epsilons, and this is same as minus 2 theta 1 theta 2. So, that tells you theta 1 theta 2 is minus half theta theta, and that is this. Again, now I could do theta 1 theta, that is this one is half epsilon alpha beta theta theta. Note there is minus sign here, there is plus sign here. That is because epsilon 1 2 is minus epsilon 2 1 is minus 1. So, that is why there is change of sign in the two. And theta alpha down, alpha up, theta beta down is same as half alpha beta theta theta. Theta alpha bar, theta alpha beta bar, alpha dot beta dot is minus half alpha dot beta dot theta theta, where theta theta is shorthand for theta bar alpha dot down up. And theta alpha dot up, theta bar beta dot up is 1/2 epsilon alpha dot beta dot theta theta, and theta bar alpha dot theta bar beta dot is 1/2 delta alpha dot beta dot theta bar theta bar. These are straightforward things. Just check once for yourself and convince that these are true. And once you have convinced yourself these are true, do the following exercise. Use these and check theta sigma nu theta bar sigma mu theta sigma nu theta bar. See, this object is shorthand for theta sigma mu theta bar is theta alpha sigma mu alpha dot theta bar alpha dot. This object is the shorthand for this. This object is same as 1/2 theta 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 bar times eta mu nu. This is contraction of two thetas, contraction of two theta bars. So, see, I would not put brackets to indicate that's how it is, but from context you know it, because there is no, you cannot make contraction between theta and theta bar. Is this notation sufficiently clear, or do you want me to put brackets to make sure that you understand? This is contraction of two thetas and contraction of two theta bars. Theta with another fermion xi and theta contracted with another fermion chi is -1/2 xi contracted with chi theta theta. Theta and xi contracted, where xi is a fermion, theta and chi contracted, where chi is a left-handed fermion, is -1/2 xi and chi contracted and theta contracted. Theta bar, xi bar, theta bar, chi bar is -1/2 xi bar, chi bar, theta bar, theta bar. You can use these to check that they are right, or you can use directly the phase rearrangement rules that we set up last time and check this is true. Let me check one for you so that you see how it is done. Which is the one? All right, let me take the second one. That's has less algebra. Theta xi, theta chi. So what is theta xi? Theta alpha, xi alpha, theta beta, chi beta. That's what it is. Write this as theta alpha, theta beta, xi alpha, chi beta. Take theta across here, but you have taken across a fermionic object, put a minus sign. Now use this property here. extra minus sign, this minus sign goes away, that's half. So this is equal. Now, write this as minus beta alpha xi alpha chi beta. Interchange beta alpha and put a minus sign. Now, this is the rule for raising the index alpha. And that's is that what we have there? Yes. Now, 2 thetas in front or 2 thetas later doesn't matter, because a pair of thetas I can take it across. It's a bosonic object. So we have some nice properties. Now we're going to introduce something, a concept, which we'll call, give it a name, an operation. We're going to introduce an operation and give it a name. Operation, introduce an operation. And give it a name, differentiation. With respect to Grassmann coordinates. We understand what we mean by differentiation with respect to x mu, the real differentiation with the real variables, because that's defined in the statistical mathematical sense as value of a function at 2 different points, and then those points coming close in some level. That's what defines a differential. But we are not defining this differential in that sense. We are using the word differential, but we don't mean it like differential operation in over functions of real variables. We mean by this word differential on Grassmann by the rules that we're going to prescribe. These rules define the difference. And we give it a symbol, d alpha or d by d theta alpha. These are symbols for this operation, which are like the symbols that we use for ordinary differentials or functions or real variables or complex variables. But they are not differentiations in that sense. And d alpha up is d theta alpha down. Alpha down is the differentiation with respect to theta up. Alpha up is differentiation with respect to theta down. And d bar alpha dot up is d by d of theta bar alpha dot down, and d bar alpha dot down is d by d theta bar alpha dot up. These are symbols for this operation. And how do these operations act? D alpha on d theta beta is delta alpha beta. That looks like a rule for ordinary differentiation, right? As if they were real variables. d alpha d on theta beta down is delta alpha beta. D bar alpha dot on theta bar beta dot up is delta alpha dot beta dot. D bar alpha dot up on theta bar beta dot down. Okay. So these rules are exactly the same that would be rules for ordinary differentiation over real functions. Now given these rules, I can check what is d alpha acting on theta beta. This rule, now theta beta is down. I pull theta beta down through my epsilon. So the answer is epsilon alpha beta. D alpha up, theta beta up is minus epsilon alpha beta up. D alpha dot bar theta bar beta is minus epsilon dot beta dot, and d alpha dot up theta bar beta dot up is epsilon dot beta dot up. Do I have signs right? Something I have done not right. All of them have minus signs. This should be minus here. This should be minus here. That is 0. Mixed ones are 0. So I have not written. All right? This implies, this property implies a rule for raising and lowering the spinor indices on the derivatives. How do I do it? This is same as delta alpha. But this is a rule, if they were ordinary spinors, then that's what the answer is. But given these properties, there's an extra minus sign. So the lowering and raising, let me write down the raising one, other one also. Epsilon beta on d beta is minus d alpha, and similarly epsilon dot beta dot d beta bar dot is minus d alpha bar. Epsilon dot beta dot d bar beta dot is minus d bar epsilon dot. So the raising and lowering through epsilon symbols acts on derivatives with an extra minus sign as compared to when it acts on the coordinates. And also, what happens if I do two operations, delta alpha and delta beta? They anti-commute. And mixed ones also. one more thing, chain rule. If I operate d alpha on a set of objects phi and chi, both fermions, here this property is different from ordinary differentials. Ordinary differentials, we will not change the sign. Here you are changing signs because these are Grassmann differential operators. That's part of the definition of this operation. Huh? Huh? That's the reason I emphasize, and we'll use the word, but we don't mean that. You could use a different name for it. Operation del. Sir, huh? Okay. You can use a different name if it's confusing. But some properties it shares with ordinary differentials, so therefore they use it. But we remind ourselves not all properties. Now do an exercise if you want to. Take dd and act on theta theta. Now what does dd? dd is a shorthand for d alpha, d alpha. Calculate this and find out this is simply 4. Or do d bar on theta bar, where d bar is the shorthand for d alpha bar alpha dot down, d bar alpha dot up. So now we have given some properties of these Grassmann coordinates that we have introduced, and we have written a superfield in terms of Grassmann coordinate, and that superfield is nothing but a collective name for a set of ordinary fields. Now what we want to know is that how does supersymmetry act on these. So the collection of objects, ordinary x mu and theta alpha and theta bar alpha dot, this we gave a name called superspace. This superspace. SUSY X on superspace as a super translation. What do we mean by super translation? Theta changes by theta plus epsilon. Epsilon is another Grassmann variable, which is the parameter of transformation. By how much amount do I make the transformation? And and changes theta bar to theta bar plus epsilon bar. And changes x mu also. By an amount I times theta sigma mu epsilon bar minus epsilon sigma mu theta bar. So SUSY on superspace is a super translation. Translates these objects by this amount, this object, and x mu by this amount. Remember, this object is a pure imaginary object. That's why it's an I here. So this together is real with an I. Now, why do we say that this is what generates supersymmetry? Is that if I were to write the corresponding generators for this super translation, which implement this supersymmetry transformation, they satisfy the supersymmetry algebra. Why did I cook up this answer? Is because the corresponding generators, which we will write soon, which implement this transformation, are the ones that satisfy supersymmetry algebra. So in this space, P mu, an ordinary space, is a translation generator, and supersymmetry algebra is Q's and P's, Q bar and P. That's what supersymmetry algebra is. So what we have done is that we have found a method of making Q's to be translation in some sense, like P mu is translation in ordinary space. Now, in what sense translation? Translation in the sense that it changes these coordinates, theta coordinates, by a translation, by a shift. Now, let me write down. So what do I mean is that under SUSY transformations, if I write it in terms of the generators, change in theta, which is epsilon, would be given in terms of supersymmetric generators or supersymmetric transformation, commutator with theta. That's what is the change in under transformation. And this object is epsilon. Similarly, on theta bar, and on x mu, so these transformation properties written in terms of generators would have to follow these kinds of rules. That Q, epsilon Q plus epsilon bar Q bar commutated with theta, so Q's are generators, should give me an epsilon. So which means I have to, if I find Q's and Q bars which does this, that will give me a representation of the SUSY algebra in the superspace. And I check what is their algebra. and on a superfield f of x theta theta bar, this transformation would act as change of the superfield, is value of the superfield at x plus transformed x See, there are two ways of writing how a particular transformation property x on any object is either you write it through the generators and as a commutator, or you write it as a representation of that object acting on the fields. So, like we said sometime, p mu on phi scalar field x is I d mu of phi x. So, generator times commutator or a representation of that generator in that field acting on the field, that is what it is. So, here I have changed the notation. This is as a representation. So, these are differential operator representation on fields. This is the general statement. In specifically on delta t, I could again write it as acting on theta. Now, this is a differential operator representation on the superspace, and that is what should be epsilon, and theta bar So, now this is the same equation as this is written in terms of generators, this is written in terms of a differential operator representations on them. So, all I have to do is find out a differential operator representation of q and q bar that gives me these results, and the answer is the following. Q alpha is minus I d alpha minus I sigma mu alpha beta theta bar beta d mu. Q bar alpha dot up is minus I d bar alpha dot minus I sigma bar mu alpha dot beta theta beta d. d alpha, alpha are spinorial indices, so it is a spinorial derivative. This is derivatives of Grassmann operators. So, little notational explanation. D mu is with respect to x mu, because mu, we have reserved mu index for space-time labels. Alpha, beta, gamma are spinorial indices. So, this d alpha is a spinorial, it's d by d theta here. This is bar spinorial derivative, the way we define spinorial derivative through its operations. It's straightforward to check that this is precisely what this is. D mu acting on theta is 0, so only piece is this one. So d alpha acting on theta alpha is epsilon, there's an I and I goes away, that's what it is. So this piece is trivial, this piece is also trivial, this piece is slightly, it needs a little bit of calculation. Because, well, not really much calculation, it's this piece that will act on that. This, this acting on this, only this much. So this is what the answer is, times an epsilon, which is perhaps this term. Is it clear? And then take the q bar, which is this, acting on this, again this piece only, it is this, and then you write raise and lower indices and kinds of things. You can convert sigma mu bar into sigma by multiplying by 2 epsilons. So that will happen, and that will give you this piece. All right. So what we have is that we have a differential operator representation of q's which implements this super translation. And then next thing is to check what is the algebra of these operators. So exercise. So what we've done is we set up saying that we define a super translation on the super space through these rules. X mu gets shifted by this amount. Then we said, can we find a differential operator representation of q's which implements that, which means this. And the q's that implement that are here. And what is the algebra of those q's? That's the same as the supersymmetry algebra. So we have found the supersymmetric transformations on the super space act as a super translation. I think we'll stop at that here.